See that? You didn't see that. It's not real. Nothing's real. You live in a simulation. Simulation theory. Look it up after this video. It'll change your life. Anyways, things are probably real, but if they're not, you can't tell, so who cares? Continue living like you're in the Matrix. All right, problem. That's another story for another time. Problem 2328, number of increasing paths in a grid. 23, Telnet, if you're from a networking background. 23, Michael Jordan. 28, the age by which I hope to be a FANG engineer. If I'm not by that age, then what am I doing this for? Anyways, that's another story. 2328, number of increasing paths in a grid. This is my first time approaching this problem. I will admit I did read it a little bit before I started because I didn't want to do a problem that I couldn't solve today. So I'm pretty sure, just off the cuff, that full disclosure, that I have a valid approach, but that's neither here or there. Let's just go ahead and get right into it. So you're given an m by n integer matrix grid. So a grid that's not necessarily square, where you can move from a cell to an adjacent cell in all four directions. Okay, so you have the freedom to move in any direction. Of course, if you're on the edges, like you're at this location here, you can't move to the left and you can't move up because there's nowhere to go. But, you know, in the case where you're in the center or something, you can move in any direction if there's a grid in that grid cell in that direction. All right, we're going to return the number of strictly increasing paths in the grid such that you can start from any cell and end at any cell. Okay, so this seems like a lot of stuff we're going to be doing. That's a lot of things that we need to compute. So the only way that there's going to be some sort of optimal solution is if there's some component of remembering previous values, likely dynamic programming, right? Start from any cell and end any cell. Since the answer may be very large, return it modulo 10 to the 9 plus 7. Now, I'm going to tell myself right now not to forget to mod my final answer by 10 to the 9 plus 7, but depending on how long this video is, I might forget, and I won't do that. But it'll get you wrong, and then I'll do it later. So this is just kind of me predicting future Ben's behavior. Two paths are considered different if they do not have exactly the same sequence of visited cells. Okay, so here's an example, a very small example. So we have 1, 1, 3, 4. The strictly increasing paths are 1. So a cell itself is a strictly increasing path, I guess. This one, 3 is a strictly increasing path. 4, 1 to 3, 1 to 4, and 3 to 4. And 1, 3, 4. And that's total 8, okay? So I hate when they give you problems and they don't have, I don't hate, I'm not a fan of the fact when they give you non-beefy example problems, but we have to, you know, make lemonade with the lemons that we're given. And then 3 and 4. So I think the thing to think about when you look at this problem is try to map it as a graph, right? And then we can think about what kind of operations we're going to do on this graph that's determined from the initial grid, right? So if we think of each cell as a vertice in our graph, okay? So we have these 4 vertices corresponding to each cell. How do we know what edges can exist inside of this graph? Well, the graph has to have strictly increasing edges in each path, right? So there's never going to be a path in the graph that goes from node 1 to node 1 like this, right? Because the path has to be strictly increasing. So no such edge could be inside of a valid path. So if really the condition is an adjacent node is a member of a valid path if it's greater than the node that you're checking, right? So when I check this node, which edges can be a part of this valid path? Dude, this delay, I'm sorry guys, there's like some crazy delay. It's Apple products, you know. Someone watching this, please get a job at Apple, because I'm not smart enough to, and just fix their products, you know. They're just sometimes they're not great. Okay. So I reconnected it. Hopefully that helps. Probably won't. It seems a little bit faster, but no, it's not. Okay, well, it's going to be what it is. Okay, so there is an edge path from 1 to 3, right? Because there is an increasing path from 1 to 3. There is an increasing path from 3 to 4. And there is an increasing path from 1 to 4. Right, because no such other path can exist within the system because like 1 doesn't go to 1, 3 doesn't go to 1, 4 doesn't go to 1, 4 doesn't go to 1, 4 doesn't go to 3, right? Because only neighbors where the from end of the neighbor pair is less than the to end of the neighbor pair, right? The from end of the neighbor pair is less than the to end of the neighbor pair, an edge will be created. And you're going to notice that this is a direct acyclic graph, right? This is a DAG because there's no such way that you can have a cycle, right? Because a cycle means that there's a system of edges where one goes to another, which goes to possibly another, and back to the original. Well, that would mean that you have something that's increasing, and it increases to the first value. But it increases from the first value to the second value. So how can the second value increase to the last value, which also is less than the first value, right? It's going like 1, 2, 3, 4, 5, 6, 7, 8, 9. It can never go back to 1 because 1 is less than 9. If that doesn't make sense, just try to derive a cycle using this approach and you'll see that it's impossible. But why does that matter? Well, one thing that's beautiful is that all dynamic programming problems, which is something that I think we're going to use in this kind of situation, can be modeled as a DAG, right? And this thing already is a DAG. So this system already is in a form where you can apply dynamic programming. So we know that we're going to be doing something with dynamic programming just because of the nature of the problem and that you can apply dynamic programming to DAGs. Why? Because it's a DAG, okay? Now, what is dynamic programming? How's that going to work in this system? How are we going to traverse nodes? Well, we're probably going to do some sort of topological sorting approach to to traverse this system. Well, why? Because it's a DAG. So if we do topological sort, we can efficiently check nodes and ensure that we don't recheck information that we've already found, and we can efficiently find information. So it's kind of like, I would call it topological traversal. It's really just doing DFS with extra steps, but we'll call it topological sort just to be fancy. And now we need and that's pretty much the whole problem. We just need to think how we're going to incorporate these ideas into this DAG, which is from the initial grid. So these three things that we're really going to do. I think the first thing you would do in this problem, even if you couldn't solve the entire problem, half of the problem is just trying to model the grid as a graph. So let's do that first. So the first step is model graph, model grid as a graph with appropriate edges. All right. Well, for this system, each vertice is a grid cell. So each vertice has a unique row-column combination. So I think that could be easily approached here. So I haven't programmed since Friday, and it's Sunday. And apparently I lose half my ability after a few days. So I might make a few mistakes here. But I think we're going to make our graph a default dict, which is a list, right? And then we're going to look at each ij pair. We're going to use the product, length of grid. So this is basically just a nested for loop. So for each ij pair, right? Okay, and then we're going to say, we're going to look at each grid, right? Item. And we're going to say for each neighbor, so for the neighbors are, call it KL in, well, I can go I plus 1 in J, right? That means I go down, I guess. I can go I minus 1 in J. That means I go check up. Right? I'm looking at each of the neighbors for any cell. So this is a cell, and these are the neighbors of that cell. These are the neighbors. This is each cell. Now we're looking for each neighbor of the cell. Right? We can go to the right, and we can go to the left. Okay, so I'm looking at each potential neighbor. Now, how do I know if this neighbor is valid in our graph? Well, the first thing is you just got to make sure you're in bounds, right? You can't like go outside of the graph. So that's the first thing we'd have to check. So we'd have to say, well, if 0 is less than I, which is less than length of grid, okay, it can be greater than or equal to 0, sorry. And 0 is less than or equal to I, Sorry, we're talking about K here because we're looking at the neighbor. So if the neighbor is in the grid, if the is in the correct range of the rows, and the neighbor is in the correct range of the columns, then it means that at least it's inside of, this means it's at least inside of the grid. But what else do we have to check? Well, what else has to be true? The grid at KL, so this neighbor's value has to be greater than the current node's value. Grid IJ, got in the way here. IJ, we'll just leave it. A little bit of my head will cut off. You don't need to see my whole head anyways, who cares? So this is checking that the neighbor has a higher value than the current node, which is a condition, right? Because you can never go to a node in a path that has a same or lower value, right? Less than or equal value, because that wouldn't be a valid path in our grid. So if all these conditions are true, then this neighbor node has a neighbor of KL, right? So KL is a neighbor of IJ. Now what we'll do is print the graph like we always do and see that it is the correct modeling of our grid, right? So we have this node 0, 0, and it has neighbors has the one sole neighbor of 1, 0, right? 0, 0 can go to 1, 0 only. That's right. 0, 1 can go to 1, 1 only, right? Can't go here because it's the same value, but it can definitely go to 4. Okay, good. 1, 0 can go to 1, 1 only. Okay, good. So it seems like, just for this very particular small example, I wish it was just a bit bigger, we're at our system matches, right? We said that this was there, that this was there, that this was there, and it seems to be the case. So we've correctly finished this model the grid as a graph portion of the problem. The next thing to think about is, well, how do we apply dynamic programming here so that we can efficiently find all the paths in the system? Well, when you deal with dynamic programming, right, you kind of like zero in to a small case and then kind of, then you backtrack from that small case. So the smallest path here, right, increasing path would be this 4, right? So this 4 is the smallest path. And when 4 is done, it'll pass back that information to 3. That, hey, I have a path of 4 here. Now when 3 is done, it's going to pass back information to 1. And it's going to pass back the information, well, what paths does 3 have? Well, 3 has itself as a path. And it has the path 3 to 4. And it'll send that back to 1. And 1 will say, oh, what path do I have? Well, I have the path myself, 1. And what's passed back to me, right? So I have 1 to 3. And I have 1 to 3 and to 4 from where I'm at. So I guess the idea is when a node is done being explored, like 4, it says, I'm done being explored. I'm going to pass back to the people who called me all the paths that I have, and they will also have the same paths as well, because I'm greater than them. Right? The idea is like, if I'm this node here, and the next person I ask is this guy here, this much bigger guy, right, with a much bigger value, and we don't know what his neighbors look like, right? We don't know what's going on here. What I'm basically doing in this problem, who knows what this system looks like over here? What I'm basically doing in this problem is I'm saying, like, hey, how many people, you're taller than me, so everybody to your right, how many of them are taller than you? right? Well, he'll respond and say, well, I have all these people and all this system of networks that's taller than me. And since they're taller than me and I'm taller than you, then they're also taller than you, right? So when 3 goes to 4, when 4's finished, all the paths that 4 have will also be valid paths for 3 because 3 is smaller than 4 because there's a path from 3 to 4. So when 3 passes information back to 1, all paths that 3 passes back to 1 will be valid paths for 1 because 1 is less than 3, and that's the reason why there's a path from 1 to 3. So the idea is when somebody's done, all the paths that they find will also be paths for people that called them. Okay? So with that idea, how this problem will basically work is we'll have a system, right? And if there's a system here, we don't know what it looks like, but we'll run topological sort. Now the reason why we're doing that is because we don't know exactly how the system works, so we don't know exactly where to start, right? But we'll just say that that for whatever reason, we started with this node here. This node will ask its neighbors, how many paths do you have? And when it responds back, I have 8 paths. How many paths does this guy have? Well, he can attach himself to all of these paths, right? Because all these paths are greater than him. So he's also a valid member of those paths, plus just himself. So he'll respond, I have 9 paths. Okay. And then he'll be done. And maybe some other node is, now let's imagine that the next one to go, because he has no more people to explore. So he'll respond, I have 9 paths. Then maybe this one goes. Right, I'm just picking arbitrarily what happens here. I'm trying to make a case that's more complicated so you can see the nuances and the edge cases where things can happen, why we're using topological sort here. When this one's done, maybe it'll get information back and it'll say, oh, I just have 1. This will say, I have 1 path. And this will come back and say, I have 2 paths. Right? Now, this is where I top sort is what we're doing here. Now, let's imagine that this one is next. So maybe it goes down this link. It gets information back. We've seen that happen over and over again. But when it goes down this link, what we don't want is to go through this entire system again. Right? Because we've already done that. So instead, what should happen is when we go to this link, here, right? This thing should, before it explores, going to be like, look, I've already done what I need to do. I'll send you back your information. Same thing when it goes here. This thing will say, I've already done what I need to do, and it'll send back its information. So we need to save information, and we need to maintain counts so that if our parent calls us later, we can give them the information without recalculating it. Okay, so with that, let's just go ahead and start the problem. All right, so we're going to do, I'm going to first just build a very traditional form of topological sort, and then we'll tweak it. So in topological sort, use a visitors array. We'll just make it a default dict. And so it's a DAG, so we don't need to worry about. Okay, so instead we're going to do, we're going to have a dynamic array. It's going to be a default dict. And the data type will be lambda -1. So this will encompass all information, because when we look at this system, we can just look at the fact as if something has determined how many paths it has, that means it's finished being traversed. So if we look at a neighbor, and it hasn't determined how many paths it has, that means it hasn't been traversed yet. If we look at otherwise, if we look at a neighbor and it has determined how many paths it's traversed, that means that it's already finished, and we can just return the information that it's saved. Okay, so that's what we're doing here. So -1 means that it hasn't been traversed yet. So that'll be the default value. Okay, so do DFS. And we'll have this vertice. We'll call it V. We'll say if D of V not equal -1, that means it's already been traversed. Then we return D of V. Otherwise, we're going to look at all of our neighbors. So we're going to say for neighbor U in graph of V, D of V. See, what we don't have to worry about is since this thing is acyclic, we don't have to concern ourselves with cycles. So I'm not going to build in that cycle feature of topological sort, and we don't have to worry about cases where things are half done because there's never going to be a cycle that brings us back to any node. So D of V equals plus equal DFS of D of V DFS of U. So we look at the neighbors' answers. And then we say D of V plus equal 1 because we are our own path. And do we return anything? Yeah, we should return D of V. Should be fine. All right, and then we'll do the same thing here. We'll look at each and every node. We'll run DFS on each node. I wonder if you do that. Okay. And then we'll return the sum of D. V is not defined. Okay. Unsupported types. Oh, because that's a, can I do that? I need to return the sum of the values, right? Oh, no. Oh, plus equal 2 because it starts at, all right, this should start at 0 then. And then we could just say if D of V and plus equal 1. All right, let's try that. Come on, believe. You have to believe. Wrong answer. I told you I'd forget. I'd forget to modulo. I told you I always do that. I know myself so well, I know when I'm doing to do something stupid. It's insane. I told you. I said in the beginning, didn't I? I said I'm gonna forget to modulo, and then I did it. It's like I'm aware of how stupid I am. That's what's so strange. The only thing worse than being stupid is being... So dumb I can't even explain that I'm dumb. The only thing worse than being stupid is being aware that you're stupid. All right, let's try that again. All right. Come on. Look at that. Magic. So what did I do here? Well, the idea is what we did before, right? Because if my neighbor has a valid path, then and my neighbor's greater than me, then it'll also be a valid path for me. Plus, at the end, I add the additional path associated with me, which is the fact that I am my own valid path, right? Me alone, I am my own valid path, right? And here is, well, if I end up encountering a node that's already been traversed, then it'll have a populated D value, right? That'll mean that it already went through all this, and we don't want to do that again, so let's just return that information here. All right, now what's the runtime of this? People have been messaging me saying, you don't do any runtime. I hate doing runtime, all right? That's the runtime. The runtime's right there. It's fast enough. But I know it's not what they're gonna want to hear in an interview. So is there anything else I need to explain? Why did I sum D values here? Well, because every node in D tells you the number of paths that starts with that node, right? And all paths is the sum of paths that start at each node for each node. So for each node, I say, how many paths start at your node? I add that up. And then I look at each node and I ask the same question, sum it up, and return it. All right, but what's the runtime? Who knows? Well, there's m by n. There's m by n edges, or m by n nodes that could have at most 4 edges. So that is constrained. So I'm not going to consider the fact that there's 4 edges per node because it's always 4. All right, there's no system where like I could have an edge that goes to some distant neighbor, right? Because I'm only dealing with adjacent nodes. So I have to look at each node and well, it's linear time, right? Because when I look at a node, I only have to look at each node once. Because if I encounter that node again, that's because it's a neighbor of a node. I don't need to do any additional information. I just return the saved information, right? So it's just m times n. It's linear time, right? Because there's m times n nodes, but there's a linear number of nodes, I guess. I mean, that's why I don't like doing time complexity. Let's see how ridiculous I am at it. And then what else? Space complexity, well, I have to save information for each node, and that's it. So that's m times n nodes. And then I guess the stack grows with DFS, so an additional m by n nodes, because I could start the stack like at the most optimal place, and I have to traverse the entire graph, and that builds in a huge stack. But there's only m times n nodes, so that can only build m times n nodes on the stack, because if I was to ever visit a node I've already visited, well, that information's already been found, so it wouldn't grow the stack more than that. So it's a linear time algorithm, but I think exponentially. Let's go. All right, guys, have a good one. Hopefully this was a little productive.